Good day everyone, I am Andrei Dita and I will be talking about the coastal engineering analysis and design of the fetch-limited storm-trapped LACUSTRINE Marina. My co-authors are Dr. Eric Cruz and the engineer Jose Carlo Eric Santos, and we are from AMH Philippines. For the outline of my presentation, I am going to start with the project background, the objectives of the study, design concept, marina layout, and hydrodynamic analysis, and then results and conclusions. From this satellite image, you can see to the right that Caliraya Lake is situated at about 290 meters above mean sea level. To the west of it is Laguna Lake with a lake water elevation at approximately 1 meter above mean sea level. Far out west is Manila Bay, which is connected to the West Philippine Sea. The flow of water from upstream to downstream is from Caliraya Lake down to Laguna Lake and out to Manila Bay. Now zooming into Caliraya Lake, we can see from the zoomed-in image of Caliraya Lake that it has a very complicated coastline and a number of land formations can be found within the main lake body. We could also see the networks of streams draining to the lake from various catchment areas upstream. The approximate location of the marina site is at east to southeast of Caliraya Lake, and the Caliraya Spillway and Laguna Lake are also shown as reference. Caliraya Lake is a man-made lake which is primarily used as a reservoir for a hydroelectric power plant catering to Metro Manila, the capital region of the Philippines. Other uses of the lake include fishing and aquaculture, and recreational activities such as swimming, water sports, and boating. Unlike other water bodies located in open seas, the lake water levels are not influenced by astronomical effects, but instead they are primarily influenced by hydrologic parameters such as rainfall and river runoffs and Caliraya Dam operations. So hydraulic structures such as the Caliraya Dam and Spillway also help regulate the lake water level. Shown here in the table are the operational water level requirements of Caliraya Reservoir, with a normal high water level at 288 meters above mean sea level and a minimum operating level of 285.5 meters above mean sea level. You can see in this slide the various typhoons which tracked within 200-kilometer radius of the project site from 1950s and onwards. So from Typhoon Kit, which occurred in 1957, until Typhoon Fengshen, which occurred in 2008. Selection of potentially critical typhoons were based on maximum sustained wind speed, minimum central pressure, and RMAX. The objectives of the study is to formulate a methodology for analysis and hydraulic design of a LACUSTRINE Marina, primarily focusing on wave climate and critical siting requirements for a fetch-limited water body, and to design a marina for a lake with high water level fluctuation. The marina structures are designed as a floating dock system instead of a fixed structure due to the high range of water level fluctuation of approximately 2.5 meters. So the floating pontoon elements are designed to be guided by vertical piles to resist lateral movement, and the wave conditions at the dock shall not exceed the wave height threshold for boat stability during prevailing conditions. And the pontoon shall be vertically sighted to withstand the heaving induced by historical typhoons that trapped the project area. Now we proceed with the marina layout. The design considerations for marina layout include the vessel specifications, boat wakes, channel depth and width, the berth requirements, turning basin dimensions, and the guide piles. From the list of prospective vessels that will use the marina, we came up with a design beam and length overall of 2.5 and 6.2 meters respectively. The draft of 1.5 meters was assumed based on Australian Standards 3962-2001, and from the recommended food number of 1.0 of ASCE for designing small craft harbors, a limit speed of approximately 4.75 meters per second can be set as the boat egress speed. Navigation within the marina should be restricted to less than the calculated limit speed. Boats traveling along a sailing line creates ship-generated wakes, which causes transverse and diverging waves to form cusp lines at an angle of 19 degrees from the sailing line. Generated wave heights and corresponding wave period near the wake source can be calculated using the given equations. H is obtained from zeta, channel depth and fluid number, and the wave period is obtained from the vessel velocity and acceleration due to gravity. A ship geometry coefficient of 1.2 is recommended, and the fluid number is computed as shown. We now compute for the channel dimensions, and we start with the channel depth. So the depth depends on the draft, Allowable wave height under kill clearance based on lake bed classification. From the design vessels, we have a draft of 1.5 meters, and from ASCE, we use an allowable wave height of 0.6 meters for tranquil boat block conditions. And for lake beds classified as clay to soft rock based on AS standards, use an underkill clearance of 500 mm. This would result to a minimum required dredging depth of 2.3 meters below minimum operating level or equivalent to elevation of 283.2 meters above mean sea level. As for the channel width, it depends on the design vessel, length overall, and beam width. So the entrance channel width is computed differently from the interior channel width as shown here from equations from the Australian standards. But due to the relatively short and narrow beam and the length overall of the design vessel, we came up with a minimum channel width of 20 meters. That is for the entrance and the interior channel conditions. You also have to account for the turning basin dimensions for vessel moving in and out of berths. The figures show two different configurations from ASCE. One is for marina exposed to winds and currents, and the other is for those with no maneuvering required. We have to include this in our design of the layout to establish a total area within the marina where dredging is required. For the guide piles, they have to be designed high enough to avoid pontoons from floating off the top of the piles under surge events. The recommended pile cutoff height is at least 2.5 meters above high water level, which in this case is at an HWL. That sets the minimum pile cutoff elevation at 290.5 meters above mean sea level, while the maximum pile cutoff elevation is 292 meters above mean sea level, equivalent to Caliraya Dam crest elevation. Next is marina hydrodynamic analysis. For the fetch analysis, we calculated the longest fetch of only 792.7 meters for winds coming in from the west direction. This is very short as compared to fetch lengths in open bodies of water. This would mean that prevailing winds could only generate very limited wind waves. As an input for the MAG 21 spectral wave simulation for ship-generated wakes, this bathymetry is generated from the Marina Layout design considerations. A dredge depth of 283.2 meters above mean sea level was observed within the entire dredge area, delineated here by the dashed line from entrance B and into the dock area. Dredging was only permitted for entrance B for other project considerations. Two cases were considered for the boat wake simulation cases. Case 1 involved simultaneous egress of boats at each entrance at elevation 289 meters for the high water scenario. And case 2 considered a sudden boat egress at an interior channel for both high and low water conditions. The wave heights and periods of the boat wakes are computed in each scenario and inputted as a wave boundary condition in the model. This is a sample calculation for case 2 at elevation 289 meters. Channel depth H is computed as 5.8 meters, and the velocity V for boundary wave input calculations was assumed at 5 meters per second instead of 4.75 meters per second. Solving for the fluid number, 0.663, the resulting wave height for the boat wake is at 1.345 meters. The corresponding wave period is 2.627 seconds. In this figure from the National Oceanic and Atmospheric Administration, you can see that for typhoons occurring in large bodies of water, the storm surge component is predominantly composed of wind-driven surge, while pressure-driven surge only accounts for 5% of the total. Due to the lack of bathymetric data for Caliraya Lake, we were not able to conduct numerical simulations of typhoons, but instead we used the following equations for wind and pressure-driven surge. When set up for wind-driven surge is computed from a Bay coefficient of 0.048 from Philippine Ports Authority Design Manual. F is the fetch length in kilometers, H is the channel depth, and U is typhoon sustained width in meters per second. On the other hand, the pressure-driven surge is represented by water level rise caused by central pressure difference at mean sea level. to a mass of water with unit weight given as 9,810 Newton per cubic meters. So the total storm surge is then computed as a sum of the wind set up and the water level rise. This table here summarizes the combined wind and pressure-driven surges of the potentially critical typhoons enumerated earlier. So the most critical values were due to Typhoon Patsy, which occurred in 1970 for both the wind setup and the water level rise. The values are at 0.21 meters and 0.44 meters respectively. This resulted to a maximum total storm surge of 0.65 meters. For the results and conclusions, we start with the boat rig simulation cases for case 1 with simultaneous boat egress at each of the entrances. Shown in the plot is the significant wave height propagating from the boat rigs at the entrances with direction opposite the receding line indicated by the given arrows. It can be seen that within the Marina dock, the wave heights only range from 0.05 to 0.075 meters. For case 2 high water level, the wave heights reach as high as 0.75 meters near the outer docks of the Marina. 0.5 meter significant wave heights are experienced at the remaining docks. During the minimum operating level conditions, the wave heights are predominantly at 0.5 meters, with some areas reaching as high as 0.75 meters. We then compare the simulated wave heights to threshold values of commercially available pontoon dock systems. Here, for prevailing continuous scenario, a threshold wave height of 1 foot or approximately 0.3 meters was assumed, while 3 feet or 0.9 meters was assumed for the storm critical event. Correspondingly, case 1, being the more common boat scenario, was assessed for a prevailing condition threshold. On the other hand, case 2 is compared with the threshold of 3 feet or approximately 0.9 meters. Both of the considered cases satisfy the threshold wave heights of the considered pontoon dock system. From the table earlier, the maximum calculated total storm charge is at 0.65 meters, which is lower than the 2.5 minimum pile cutoff height. Hence, the recommended pile cutoff elevation is at 290.5 meters above mean sea level. In conclusion, simulated boat waves resulted to wave heights within the marina satisfying the trunculated requirements for small craft harbors and threshold wave heights for pontoon docks. Due to fetch limitations of Caliraya Lake, pressure-driven storm surge was found to be the more dominant surge component. However, the pile cutoff height is still governed by the prescribed minimum height above the high water level, not by total storm surge. And lastly, the code-imposed minimum dredging depth is sufficient to promote wave heights of penetrating wind waves throughout the marina zone that do not exceed the threshold for the design boats. Here are the references used for the study. That's all. Thank you.